Good morning and welcome back to Math and Engineering Help Desk. Today's video is about concept of proportional and linear relationships and the comparisons between those two things. As you know, this lesson does kind of line up with the Illustrative Mathematics curriculum, Unit 3, middle of Unit 3-ish, which students will have taken about 4 or 5 days on proportional relationships. And today's video is going to kind of transition into the concept of linear relationships, which have a lot of similarities to proportional relationships, but obviously a couple of main differences. So here on this page, I've got two examples of, of both. So on the left, we've got a situation where a student is saving $40 a week from their paycheck to afford a new game system. Now, this is a proportional relationship because every time 1 week goes by, the amount saved will increase by $40. So if you think the proportional relationship y equals kx, in this case, you're given a unit rate, so the situation that models, the equation that models the situation is y equals 40x. So for every week, which is x, you get $40 y saved up. X equals weeks and y equals money saved, right? So also keep in mind that when you're thinking about proportional relationships, it's important to identify x and y, what they mean, so you can understand what the equation is telling you. So when you have x weeks, you multiply that amount of weeks by 40, and that would equal the amount of money y that you save. Similarly, this 40, which is k, is a comparison of y over x. So the units of this is $40 money per week, $40 per week. And if we wanted to graph this, we can do so. We can graph this with let's graph this with a blue line, and we can draw a graph basically starting here. And if I were to give myself some intervals, basically if I put a 1 here, I could put up here a 40, and I know I'm just kind of mousing this right now, which is okay. That would be a 40. And that would basically be a graph that would represent the situation of saving $40 per week. Now, a couple of key ideas with proportional relationships. Number one is that it's in this format of y equals kx, but also it is always a graph that starts and goes through the origin. Okay, so, and we also think about proportional relationships typically with positive values, although technically it is possible to have a negative k and have a graph that doesn't go through the first quadrant but still goes through the origin. But we're going to stick to the real life situations where that might be the case. So anyway, you know, what we're talking about here is if it's a proportional relationship, it fits y equals kx, and I'm also going to use y equals mx because, you know, we can think of the k as a slope as well. And number two, the graph has 0, 0 as a solution. Okay, so in other words, the line travels through the origin. Okay, so that's what a proportional relationship is. Now, on the right side of this image over here, I've got this picture of a couple of stacks of styrofoam cups. Now, this image, by the way, thank you very much. This is from Lesson 5 from the Illustrative Mathematics curriculum in Unit 3, Grade 8. So here we've got some cups, and we've got a ruler so you can get a measurement. And you'll notice that there are 6 cups in this stack, and in this stack there are 12 cups. Now, if this was a proportional relationship, the height of this stack of cups would be half the height of this stack of cups. Well, this stack of cups is approximately 15 centimeters high, and this stack of cups right here is approximately 23 centimeters high, right? So we can tell right away that 23 divided by 2 is not 15. So this would not be considered a proportional relationship because the relationship between this and this is not the same value, okay? If it was proportional, then this height right here, this 12 stack height of cups, would be twice the height of this stack cup of 6. So it's not considered a proportional relationship. However, if we consider what happens when we add 1 to each, 1 cup to the stack, the height does increase by a constant amount. So you'll notice that right here, every time I put 1 cup on, I'm getting a little more than 16 centimeters in height. And then I put another cup on, a little more than 17 centimeters, but close to 18. And then right here, it looks like exactly 19, right? So it went from 15 to 19 in 3 cups. which is a change in height of 4 centimeters. And that was with 3 cups, right? So if I were to make that into a unit rate, that would be 4/3 centimeters per cup. 4/3 centimeters per cup, right? So notice that the change is constant, just like in this situation with this proportional relationship here. The change per x is the same with y. However, what's different is that it still doesn't quite fit the bill of it. If we were to graph this, it wouldn't go through the origin, right? Well, if we were to graph also, one of the things to realize is that one of the solutions would certainly not be true. But let's take a look at what a graph of this would look like. Let's put these 2 points on here, 6, 15 and 12, 23. So let's go to a graph. 6, 15, here's 6 and here's 15, right about here. Make sure about that. I think so. 15, 14, 13, 12, 11, 10. Yep, that's right. 15, so 6, 15 is right here. And then here's 12, and here's 23, right? So here's the 2 points that I can use for reference, right, between these 2 points. Now if I grab my line tool and I draw a line, let's start it at this point here and extend it through there, and I'll extend it later. So we can see here, that's a pretty well-placed line right there. And if I were to continue this line all the way through this graph, that's what it would look like, right? So every time the cup height increases, it does increase at the same rate per cup, right? So it looks like a proportional relationship, but the key difference here is that this line is not hitting this point here, right? So because it's not hitting the origin, this is not considered a proportional relationship. However, it is a line, so we do call this a linear relationship, okay? Now, a linear relationship is, well, we think of it this way: a proportional relationship is a subset of linear relationships, okay? Basically a situation where a graph of, or a solution set of points that satisfy x and y, x comma y, would be a line, right? So every time we add a cup to the stack, we get an extra centimeter or extra 4/3 centimeters in height. So it does fit the bill of being a linear relationship, except it's not proportional because it doesn't pass through the origin. Now, why is that? Well, if we look back at this image, notice that the first cup starts off right away with just about 8 centimeters. Okay, it's close to 8 centimeters. The first cup is 8 centimeters, and then after that, we are 9 1/3, 10 2/3, and 12, right? Something like that. Okay, I know I'm a little bit off with that. Maybe it's 7, maybe it's something like that, right? So the starting height is not 0, right? When we had 1 cup in the mix, that cup already adds and starts off with about 7 or 8 centimeters of height. 7 1/3, 7 1/2, something like that, right? So then the reason why the height doesn't increase the same amount practically is because each of these cups fits inside, right? These cups nest. So only the tops of the cups, the rims of the cups, are exposed once you stack them up. So obviously you're not getting the same increase every single time. So if I go back to my graph, you'll notice that right here, 1, 2, 3, 4, 5, 6, 7, just about 7. Yeah, okay, so according to this graph, it's 7. So 7 is the height of sort of a 0th point, right? And then the first cup, when 1 cup is on the stack, the height is 8 1/3, right? 8 1/3 centimeters. And then it's 9 2/3, and it's 11, right? So it kind of makes sense practically, but obviously another thing to think about is if there's 0 cups, how the heck is the height 7, okay? So in this case, practically 0, 7 is not a solution to this line, but every other point is a solution. So basically, if we kind of took this line and we just kind of changed it, I can't change it right now because I put it on here, but if we were to put it in a correct spot, right here would be that spot, right? So starting here and then going up, that would make more sense. But obviously, I wanted to show you the concept of linear relationship anyways. So, last point I want to make is this. I'm going to use Desmos to show it. Okay, so let me go to my Desmos graphing calculator. So here I've got 2 equations in here, y equals 3x and y equals 3x plus 5. Okay, so notice the difference between these two. This is a proportional relationship which travels through the origin, just like this red line shows, whereas this one here doesn't travel through the origin, but it does travel through y-axis at 5, right? So 3x plus 5 and 3x They're related. They are similar lines, except this line here travels through a different point on the y-axis and also a different point on the x-axis, but we won't worry about that right now. However, here, notice that it is, right? So 3x and 3x plus 5, this is a proportional relationship. This is a linear relationship, okay? So I want to close off this video with just one little point we'll obviously see in the future videos as well. A proportional relationship fits the bill of y equals mx. A linear relationship has the same properties, except there's a third value called b, and that b is called the y-intercept, okay? So we'll see this in the future about when we start getting into other concepts and other linear relationships, okay? The y-intercept here, we can think of this as sort of a starting value, okay? Anyway, this is the end of this video, and I want to thank you for making it to this point, and I hope that you're subscribed to Math and Engineering Help Desk. As mentioned in my most recent video, we just crossed 500 subscribers, so thank you so much. I'm hoping for 1,000 and obviously beyond, and I want to continue to help you with your math and engineering needs. Hope you have a wonderful day. Don't forget to be awesome.